Hello, and welcome to In the Lab with Nuclear Scientists, Critical and Subcritical Assemblies. I'm Janice Lindegard, K-12 Program Specialist for the American Nuclear Society. I'd like to welcome you to In the Lab with Nuclear Scientists, Critical and Subcritical Assemblies. This event is part of our educator training program, specially developed for elementary through high school teachers. I'm pleased to introduce this webinar. It's the first in a series on tools that nuclear scientists use, how they use them, and applications of their discoveries. Before I introduce our moderator, I have a few quick announcements. Please type your questions in the Q&A function. We will try to answer as many as possible following the presentation. This event is being recorded. You will receive a link by email tomorrow. Certificates of attendance are available. Send a request to askanything@ans.org. If you are an educator and would like an ANS member to visit your class in person or virtually, you can also send a request to askanything@ans.org. ANS members, our Nuclear Ambassadors program offers you free training in K-12 nuclear education outreach. If you're interested in training for your organization, contact my colleague, Uchenna Azibe, and I will put his information in the chat. Finally, we ask all participants to adhere to the ANS Code of Ethics and Respectful Behavior Policy. You can find it on our website, ans.org, and I will also drop it in the chat. Now, with that out of the way, I'd like to introduce our moderator. Evan Gonzalez is a computational physicist at the Lawrence Livermore National Laboratory, where he writes code to simulate radiation's interaction with matter. He received his undergraduate degree at Texas A&M University in 2017 and his graduate degrees, all of them in nuclear engineering at the University of Michigan in 2023. Welcome, Evan. Please introduce our presenters.
Thanks, Janice. Okay, I'm going to go in alphabetical order and introduce our presenters. They'll each talk for about 10 minutes, give a presentation of what it is they do, and then we should have plenty of time in the end for questions. So I'm going to begin with Dr. David Ames. David received his MS and PhD in nuclear engineering from Texas A&M University in 2006 and 2010. His focus was on the design and performance of advanced reactors and fuel cycles, utilizing uncertainty quantification and multi-objective optimization techniques. And I knew most of those words. David started at Sandia in 2010 and supported the NASA Fission Surface Power Project and other advanced nuclear fuel cycle projects. In 2017, David joined the Critical Experiments team and authored 2 benchmark evaluations designed and performed at Sandia. He also supports the Sandia NCS program as a NCS Nuclear Criticality Safety Engineer and Deputy Program Lead. David recently took over the role of the DOE NSCP Sandia Site Manager. Next, we have Dr. Kelsey Amundson. Kelsey earned a Bachelor of Science degree in nuclear engineering from the University of Wisconsin-Madison in 2016 and a Master of Engineering degree in nuclear engineering from the University of California at Berkeley in 2019. Kelsey began working in Los Alamos at Los Alamos National Laboratory's Advanced Nuclear Technology Group in June of 2020 as a research and development engineer. Her team operates the critical assemblies at the National Criticality Experiments Research Center, NCERC, and she is a crew member on all 4 assemblies. Before working at Los Alamos National Laboratory, she worked at the Defense Nuclear Facility Safety Board. She's an active member of the American Nuclear Society, serving as the immediate chair of the Young Members Group, and as a member of the American Nuclear Society Board of Directors, and serves on 2 working groups for ANSI/ANS 8 series standards, 8.19 and 8.20. And finally, a personal friend of mine, Jesse Norris. Jesse is a nuclear criticality safety engineer at Lawrence Livermore National Laboratory, where he has worked since 2017. The focus of his work is on experiment design, execution, and benchmarking for the United States Department of Energy's Nuclear Criticality Safety Program. Most recently, this includes 2 critical experiments within the Thermal and Epithermal Experiments Program, utilizing highly enriched uranium. and hafnium. Jesse has a Bachelor of Science degree in nuclear engineering from Texas A&M University, whoop, and a Master's of Engineering in nuclear engineering degree from University of California, Berkeley. And so with that, I believe David is going to be presenting first, and so I'll let him present and share his screen.
Right, let me know if everyone's seeing my screen.
Looks good.
All right, thank you. Thanks for the introduction. I'm David Ames from Sandia National Laboratories, and my presentation and slides today are really focusing on the Sandia Critical Experiments Program. But before I get started, I wanted to give a little bit of background about the overarching program that funds, supports, and directs this work, and why we do it and why it's important. And also to start out with, I'd like to define a few terms that you'll hear us use throughout these presentations. So that will hopefully help people understand better what we are talking about. So the first one, it's in the title of the slide, it's critical. So there's a number of different definitions in the dictionary for critical, but what we're talking about here is what we typically use as nuclear engineers. So it defines the ability to sustain a nuclear chain reaction. And for it to be critical, we're looking at fission events that would happen in, say, enriched uranium or plutonium. And one of these events then causes a subsequent one, and so forth and so forth. So to be at critical, each one of these events would cause exactly one after it. So it remains steady over time. But in reality, we rarely see an exactly critical case. So typically, we'll talk about subcritical or supercritical systems. So subcritical, this is when that rate, so those number of fissions that happens sequentially, decreases over time, and the rate will die out as time goes on. And this is opposed to supercritical, where we then see that rate increasing over time. And this is important because that rate at which it does increase can be very quick, where it's hard to or impossible to control that type of reaction. You get very large power excursions. So now we defined critical and subcritical and supercritical. This really helps lead into a discussion about nuclear criticality safety. And this is important because it has a strong tie to the work that we do. And nuclear criticality safety is really involved with the nuclear safety outside of reactors and assemblies. Because in reactors and assemblies, they are designed to go critical, but outside, of course, that is not the case. And that's where nuclear criticality safety comes into play. So there are a lot of operations and processes that are up for some consideration for nuclear criticality safety. And not only are we talking about normal conditions, but also off conditions or abnormal conditions where there's upsets or accidents, or there could be earthquakes, mistakes, whatever it may be. So you could quickly realize that there's really countless possibilities, and nuclear criticality safety analysts, they need to analyze these different processes and operations, and they rely heavily on computer codes to simulate those conditions and then to set parameters to keep the workers safe while they're doing this work. And so you might ask, how do we trust those results? Especially the analyst or the person doing the work, how confident are they that those results are correct, or how close they are to correct? Are they conservative? Are they non-conservative? And what sort of uncertainty is associated with it? So that's really where critical and subcritical experiments become very important, because those codes are then benchmarked to experiments that are performed with these assemblies. So it provides that means to tell how well they are doing and what sort of safety margin may be needed to be included with those safety parameters. So as you imagine, there are gaps that exist, and those are really, we try to target those with these experiments to fill those gaps. The critical and subcritical assemblies, as I mentioned, are used to perform these experiments. So this also leads to another question of what exactly is an assembly. So it looks and acts a lot like a nuclear reactor, but there's a number of differences that sets it apart, and so much so that we choose to use a different name for it as an assembly. So first off, one of those main differences is the size of the assembly. It is much smaller than what you typically see for particularly like a power reactor. So it's much smaller, much less material, a lot less complex. The control system for it is simpler. It also, assemblies operate at close to zero power, and a lot of times are defined as zero power. So this is important too. We don't need to have heat removal systems for the assemblies. Also, there's very low burnup of the fuel. So the amount of fissions that occur make it much easier to deal with the fuel. It can be handled. It doesn't have the same radiological concern of fuel that comes from reactors. So, and then this leads to what I started with, was the program that supports this work and directs it. And that's the U.S. Department of Energy Nuclear Criticality Safety Program. And this is a very important program to them. There are only 2 existing critical experiments programs in the US, the one at Sandia, and then also out in Nevada, which Kelsey and Jesse will be talking about later. So it's very important to maintain these capabilities. In the past 30 or 40 years, a lot of these assemblies have been shut down, and it's really hard to restart them once that happens. And also there's a lot of specialty and experience that goes into operating these facilities that we don't want to lose that as well. And so with that, I'll open up the forum quickly to Kelsey and Jesse. I tried to give a concise overview, but perhaps I missed some things. I'll let them jump in, add in where they see fit. And I know Jesse, he's come up with a few really good analogies that perhaps he'll share now or when he's talking about the Livermore program.
David, it looks like your slides actually weren't changing when you were talking. If there were anything important, maybe we could show them, but if not, then we'll just go on to Kelsey, I suppose.
Yes, thanks for that, Evan. I actually did not have slides prepared for the intro, so hopefully they'll advance as we move on.
Excellent.
All right, I'll jump in then. So the Sandia Critical Experiments Program. This first slide is kind of an advertisement for Sandia National Laboratories. Sandia grew out of the World War II effort to develop the first atomic bombs. Today, keeping the US nuclear stockpile safe, secure, and effective is a major part of Sandia's work. But the role has evolved a lot in the last 20 to 30 years. And so there's a lot of different R&D programs that are current at Sandia now. Some of those are listed on the slide here in blue. So there's a varied amount of different R&D programs at Sandia. The workforce, we're getting close to 17,000 total employees. There's a breakdown here showing the different disciplines, a lot of engineers, electrical and mechanical leading the way, other engineers like myself, nuclear, chemical, system engineers, and so forth, and then some of the sciences and maths. Also the degrees earned, just showing here a large portion are advanced degrees or master degrees, but also a large amount of bachelor's and PhDs as well. And Sandia has a few different sites The main one is located in Albuquerque. There's over 700 buildings, and it's on a large area that's on a Air Force base. There's over 14,000 acres. So the Critical Experiments Program, we're located at the Albuquerque site. More specifically, we're in Tech Area 5. So this area is set a little bit of ways. It's off in the desert. It's about 7 miles from the main campus. Of course, there's reasons for this, and that's tied to the long history of reactor operations out at Tech Area 5. And I'll be talking about the Sandia pulsed reactor facility, which is a picture shown on the top here of that facility, which was originally built to house a pulsed reactor. But about 15 years ago, that pulse reactor was sent off and is no longer active at Sandia. So since that time, this facility has housed the Sandia Critical Experiments, which below you can see that's within this dome building is the critical assembly. This is early on when it was being built, showing the tank and then the dump tank. I'll have some other slides, so I'll talk more about that as we move along. So I already talked about the purpose for designing, performing, and publishing critical benchmark experiments. Also an important item that we provide is a hands-on training for nuclear criticality safety. This is very important because nuclear criticality safety engineers are required to become qualified, and this is usually about a 2-year process, and a lot of them are required to take this hands-on training. So we perform 3 or 4 of those a year, and those are also performed out at NSCP. And again, all this work is supported by the Department of Energy's Nuclear Criticality Safety Program. So a little bit about the fuel and the design of the critical experiment. First off, we used low enriched uranium in the form of fuel rods. We have 2 different fuel enrichments, one at 6.9% and the other at 4.3%. A moderator is needed because this is low enriched fuel. The moderator is needed to drive it critical. Water is used as the moderator and also as the reflector. And one thing of note, all of the fuel that we have combined, the 2 different enrichments, would not physically be able to go critical without having some sort of moderator. This is a CAD drawing, and then next to it, an actual photo. So this is showing today what the critical assembly looks like. One of the main features is the dump tank, where the water is typically stored, and then the assembly tank. And so this is where the fuel, the control elements, the detectors, the materials we're testing, and so forth are placed within this assembly tank. And then water is filled from the dump tank into the assembly tank to drive it to those critical configurations. You also notice a walkway around it. This is used by our operations. They're always removing, adding fuel, building to the configurations that we're looking at for the experiment. And also it's used by the hands-on classes. The students are able to gather around the assembly tank and load and unload fuel as part of the class. This is an example of some of the different experiments we've done. This is now looking at a CAD drawing where you can see through the assembly tank and see these grid plates that help keep the fuel spacing and in place for the experiments. This one on the left was a set of experiments we did about 2 years ago. IRSN from France was involved in these experiments. They were really interested in the material that was placed within these grid plates and how it performed and how it affected criticality. Then to the right, it's just showing again a different set of grid plates, so a different pitch on these, and a central test region where it's dry and test materials can be placed in there to look at a target energy group for that material. This last slide showing a few more photos. The top one to the left is the 6.9% fuel. See these fuel rods have about a 1/4 inch diameter on them, and that can be compared to below the lower enriched fuel, which has about a 1/2 inch diameter, so a lot thicker. For this set of fuel, we have about 500 fuel elements available for experiments. For the higher enriched, we have about 2,200 fuel elements available. Middle picture showing here preparing for operations. The facility supervisor is looking at the fuel load, making sure everything is correct. And this is all done before they clear the room and add water to the tank. Picture below came from just a few weeks ago. These core internals or tank internals were switched out for new grid plates. You'd see the central test region here. Jason here is checking some of the fuel rods, making sure they fit correctly, the safety element, making sure it moves correctly within the core as we set up to perform a new set of experiments. And then the far picture here, this really gives a scale of the assembly and of the fuel elements. And you can see John here loading one of the fuel rods into the assembly. This here, again, a different set of grid plates at square pitch. So there's been a number of different benchmark experiments we've performed according to the fuel type, the grid plates, and the material that is in the assembly. So that concludes what I had to present. So I'll turn the time over to Kelsey to talk about NSCP in Los Alamos.
Okay, give me 1 second so I can switch sharing screens. Okay, we'll give it 1 second and hopefully everyone is seeing a screen now.
Looks good.
Okay, perfect. So David talked about Sandia's critical experiments facility and mentioned that Sandia and what I'm going to call NSCP, so it's the National Criticality Experiments Research Center, those are the only two critical experiment capability or facilities in the United States, and very few of these exist around the world. So David mentioned that there's a lot of collaboration to use these facilities. He mentioned that we have colleagues in France, and we work with a number of international partners to execute these experiments. So the facility at Sandia mostly relies on water to help the assemblies go critical. NSCP is a little different, and we are what we call a general purpose critical assembly facility, which means that we have a large amount of versatility in the different kinds of experiments that we can build. So the facility, NSCP, is located at the Nevada National Security Site, formerly known as the Nevada Test Site, and is operated by Los Alamos. So our team will travel from Los Alamos in New Mexico to operate these assemblies in the desert of Nevada. So David did a really good summary of the difference between critical, subcritical, and supercritical, and we perform all types of operations at NSCP in these different regimes. So the first I'm going to talk about is the subcritical assemblies, which we call radiation test objects, basically just because they're objects that produce radiation because they're nuclear material. So we have a large inventory of nuclear material, from different enrichments of uranium to plutonium to some more unique materials like neptunium. Then we use these to test detector systems. So there's a lot of different radiation detectors in the world and new ones being developed. So fortunately, we have a lot of items that are well characterized. We know them very well. So we will bring in these new detector systems to see how they respond to the radiation produced by these devices. And since we know what the answer should be, we can tell if the detector, if the detector's answer is different, there's probably something wrong with the detector, and they can go back, make changes, update it, and then try again later. We also use this for nuclear data measurements. So like David mentioned, that this all goes into this various safety analyses. So we are constantly trying to improve our understanding of nuclear interactions in nuclear material and the material surrounding it. So we will perform these kinds of measurements that may be subcritical, so that neutron population, decreasing over time. We will perform these measurements here to get a better understanding of those interactions that are happening. We also, at NSCP, also do hands-on training courses. So it's very beneficial when you operate in a subcritical state, because that allows people and humans to interact with the nuclear material. So during our hands-on classes, people will get the opportunity to hold and handle this nuclear material and make changes to the system safely. So I just have pictures of two different kind of sets of objects we have. The upper picture is a picture of what we call as the burp ball. It is a plutonium ball that's about the size of a softball and is 4.5 kilograms. Then the bottom picture is a series of highly enriched uranium shells that vary in mass so that we can basically build almost any spherical system that we want with them. So the next thing I'm going to talk about is our critical assemblies. So these are the assemblies that allow us to achieve that state of critical or supercritical. So we have 4 different assemblies at NSCP. They are Flat Top, Planet, Comet, and Godiva. So as you can tell by the pictures shown here, Flat Top and Godiva are what we would call set assemblies. So they are tied to a specific arrangement of fuel that can't really be changed too much. Both of them have sample regions that we are able to put different nuclear material in to make small adjustments and do studies, but the majority of the fuel is the same for every experiment. Whereas Planet and Comet are versatile assemblies that basically divide our experiment in half, and one part is placed on a stationary platform, the other half is on a movable portion, so we can build these assemblies safely, and then we leave the building and can bring them together remotely with no one else in the building. So to go through each assembly in a little bit more detail, the first one I'm going to talk about is Flat Top. It is a metric ton of natural uranium that's on the outside, and then the core can be changed to be either a highly enriched uranium core, so this is a core that has more uranium-235, which is the nice isotope that allows for fissions. And then we also have a plutonium core. So that's the big change that can be made with this assembly. And I say that this is a metric ton of natural uranium, but when you see the assembly in person, it is about the size of a large beach ball. So it's a very compact system. And this assembly was designed in the 1950s to be a very simple assembly to model with the computational tools available at the time, because it's essentially 2 spheres. So we use this assembly for a lot of different things on top of training applications that we've talked about. So when there's new material being considered for advanced reactor concepts or in any nuclear process, that we can take small components of that material and trade other pieces within our sample region to see the impact on the assembly, to help the safety analysts in the future decide how they should account for that material in their analysis. We also do various studies, so related to criticality accidents. So there have been accidents throughout the history of criticality safety. So one of the things that we can do with this assembly is basically simulate one of those accidents in slow motion. It allows us to train people to see all the physics that happen over the course for this experiment. It would be over the course of 10 minutes, where in an accident, it might happen in less than a second. So it allows us to see all of that and have people understand what happens. We also do a lot of just different detector testing with this as well. Our next assembly, Planet, is a vertical lift assembly like I described earlier. This is our smaller assembly of the two. So we use this to do our critical mass studies. So as I said, we get new materials that we think can maybe go critical, that we will want to try and test and build an assembly that goes critical. And this is one of the assemblies that allows us to do that. And we use this with unique materials. So we allow our special nuclear materials, so our plutonium, uraniums, and combine it with a bunch of other materials that different applications are considering, like advanced reactors have a lot of new things they're trying to bring in to either help with those neutron interactions in the reactor. Our experiments help them understand how those are going to work on a smaller scale before it goes into their reactor. So the pictures I have here are just 2 of the experiments we've run, the top one being those highly enriched uranium shells I showed earlier, just built into a critical assembly. And the bottom is one of our latest experiments that involved unique geometries of plutonium. So we were actually able to safely build a critical assembly with about 110 kilograms of plutonium. So it's just because of how we changed the geometry that we were allowed to do that. So that's some of the things that we will investigate in these experiments. Comet is very similar to Planet, it's just larger. So while Planet can maybe only hold 2,000 pounds, Comet can hold 20,000 pounds. And the applications are very similar, but some of the larger assemblies, for larger reactor projects, we need this larger assembly. So the bottom picture is a collaboration we had with NASA on a potential space reactor to power a colony on Mars. And the last assembly I'm going to talk about is Godiva. Godiva is what we would call a burst reactor assembly. So it allows us to operate in that supercritical regime in the areas where that neutron population is rising incredibly fast, so fast that it's really hard for humans to interact and stop anything. But it was designed such that it would shut itself down once it got to that point. So one of the unique things we do with this is, since it can simulate a criticality accident, a lot of process facilities have criticality accident alarm systems. So we will bring those systems into our facility and perform a burst on Godiva and see if the alarm system registers that there was an event to test to make sure that they work. We have also done a variety of dosimetry comparisons and testing. So every person who works with radiation has to wear monitors to monitor how much radiation you're receiving while you're working and keep track of it throughout your lifetime. So we will also use assemblies like this to test that those are working properly, and that if they get a set amount of radiation, that people analyzing them can determine what dose or how much radiation they got. So we've actually done full scale, like simulating humans. So you can see the mannequins in the picture there, that we expose a bunch of these monitors to radiation, as well as things that simulate a human being. So we can see those effects safely and ethically. And that ends the summary of what NSERC is capable of. And I'm going to pass it over to Jesse as one of the people who frequently collaborate with us on experiments.
Yes, thanks, Kelsey. Here, let me get my. All right, let me know when you guys can see.
Looks good to me, Jesse.
Great, thank you. Yeah, so I'm with Lawrence Livermore National Laboratory. I'm going to discuss some of the experiments we do with NSERC and also some of the capabilities that we have at Livermore. All of our capabilities are subcritical systems. And, you know, when we go to describe the difference between like a subcritical and a supercritical system or a critical system, you know, it tends to be a hard concept to teach and talk about. You know, when I tend to talk about it, I tend to do examples like a subcritical system is kind of where you want to be operationally. You know, if you have to interact with the fissile material, you know, it's safe, no reactions are going on. In a critical system, you know, this is like an operational reactor. It's one of these critical assemblies during operation. And then a supercritical system is like it's a criticality accident, that kind of situation. And so an analogy that we kind of discussed beforehand is you can kind of think of it maybe like a fire. A subcritical system is maybe like a smoldering fire where, you know, a reaction is going on, but it's not going anywhere. And then a critical system might be something more like a burning flame. You know, a fire that's actually self-sustaining, you know, it's reached enough temperature to keep itself going. And then finally, a supercritical system might be something like a flashover, you know, something that happens very, very quickly in a short period of time. You know, so building off kind of that analogy, what we're looking at here is like the combustibles in the fire would be similar to maybe the fissile material in our critical assemblies and subcritical assemblies. And the heat being produced by the fire is similar to the neutrons that are being produced by the nuclear reactions. But kind of going off that, let me introduce some of the things we do at Livermore. Let me get my slide. There we go. So first I want to talk about the TEX program. So this stands for the thermal epithermal experiments. And these are actually examples of experiments that we put onto the machines that they have at NSERC, specifically the Planet Vertical machine and the Comet general purpose critical assembly machine. And what these are really test beds. What we've designed are a plutonium-based system and a highly enriched uranium-based system that we have we've measured and documented, and we know to a very high level of detail. And those two systems form a baseline of these experiments. And so the next step that we can take from there is we can start to incorporate materials of interest. That's so far the materials that we've looked at are things like tantalum or hafnium and lithium. These are materials that we use in nuclear, but aren't necessarily well known, or there are concerns with the nuclear data that actually underpins the modeling of them. And so what we can do is compare our baseline to just incorporating this new material. And you can really tease out what the effect of that material is. And the next step that you can go to is actually modeling it and comparing it to comparing your model to your experiment. And depending on how well you predict, having these cases as a validation kind of shows you where you need to put interest, or maybe where something might be going wrong. And so a few of the pictures I have here, and it is a very busy slide. I wanted to include as many photos as I could to illustrate this. But what we have on the bottom left is a configuration on Comet. This is with some highly enriched uranium plates. The square configurations use plutonium zipper plates. These are on the Planet configuration. And this photo in the middle is actually an interesting one. This is actually a photo of one of the experiments during operation. So this is a critical assembly that we were able to get a photo of through a separate camera. So it's a very interesting thing to have a photo of. This is where the self-sustained neutron chain reaction is going on right now, and we're measuring it. And then the final pieces of text that I have here are a new experiment where we're looking at low temperatures. And so on this bottom hand photo on the right, we have a vacuum chamber where we're actually going to put these highly enriched uranium plates in and pull a vacuum and then cool them down to provide validation cases, and really just to see how well our methods and codes predict at these low temperature configurations. So moving past those experiments, next we have the training assembly for criticality safety, what we call TACS. And so this is actually a subcritical assembly that we have at the device assembly facility for training. And it really is a hands-on experiment. You'll see a couple of the photos I have here are students and operators interacting with the experiment. This one's made of hemishells of highly enriched uranium. And the really unique thing here is, you can really get your hands onto the nuclear material, and you can begin to see, different kinds of experiments. We can do things like approaches to critical by fissile mass, reflector or moderator, also separation. And you can begin to see how these parameters are affected by this fissile material. It's something even where you can be measuring the neutrons coming off of the assembly and just add your hands, and then you can notice that the neutron rate increases just by you interacting with the material, which is a really powerful way to kind of show this, especially to operators and new students, because it's for many people, it's their first chance to really interact with this material kind of firsthand and really see the response, for something that's kind of a difficult concept to understand otherwise. And so next up, we have our inherently safe subcritical assembly. This one is actually on site at Lawrence Livermore. So it's it's not in that high security, high hazard facility. And similarly, this is a hands-on experiment using highly enriched uranium. This time, instead of in a hemisphere shells, these are in they're really just in fuel assemblies. And so this configuration can have up to 9 of these, which I have shown there, pictured on the bottom right and on the bottom left. And then also some of the members of my group introducing some of those fuel assemblies to the tank. And so this is another really powerful one because, again, with it's just on site at Livermore. So, we can get a lot of visitors that come in. We partner with a course at UC Berkeley where the students will actually come on site and perform a set of experiments using this configuration, which again, it represents, students and visitors being able to actually interact with the fissile material and see how this changes over time, how engaging with the fissile material and actually performing the experiments with them, kind of what you can learn about, just neutrons interacting with fissile material. And then, yes, on the next slide, I have many more photos, just kind of showing, the level of engagement that you can get with this experiment. And then finally, the last type of experiment that I want to talk about is the pulse neutron die-away. This one's actually a unique experiment because for this technique, you actually don't even need fissile material. And so you can do it with just moderating material. And the whole point here is you have a target and you have some kind of source of radiation. In this case, a neutron generator is used. And you pulse that neutron generator and you see how the neutrons interact with the material. In this case, and what I have photoed here is a piece of plastic. And you can measure it over time and see how the neutrons leak out of the system, which can give you information that you can then go on and model to form the basis of, your prediction versus your actual measured result. And then another thing that you can couple with this kind of experiment is Lawrence Livermore has a low scatter facility, which is really just a large room. It has a false floor, meaning that the floor is just grates, and there's just more empty space under it. And the whole point there is what you really want to do is reduce your room return and background to get the highest fidelity experiment possible. And yeah, really, in the end, the whole goal of all these experiments is really the validation and also the ability to benchmark the methods and the codes and compare against your calculated result. And yeah, that was all. So I will hand it back now to Evan.
All right, great. Thank you, everyone. So we do have a good handful of questions here in the Q&A, and I'll try to distribute them out to all 3 of you. But if we don't get to them, feel free to answer them by typing a response to them in the Q&A function. But we have one question that was asked while David was presenting, and this comes from Michael Sinclair, and Michael asks, do these kinds of assemblies use only uranium and or plutonium, or are other fissionable materials used or tested? Great question.
David, did you want to grab that since it came during your presentation?
Yes, yeah, and at least from Sandia's critical experiments program, we only used low enriched uranium. And I think Kelsey maybe mentioned a few other materials at NSCP. Do you want to answer that, Kelsey?
Yes, so you are correct that most experiments primarily use some enrichment of uranium. So that's the variation in the uranium-235 or amount of uranium-235 in the assembly, or plutonium. However, we have done critical experiments using neptunium is one of the unique materials that we have used that in combination with highly enriched uranium.
Yeah, and to add a little bit onto that, the reason you see a lot of these highly enriched uranium or uranium systems and plutonium systems is that's really what the material used in the DOE complex, so it's really where the most effort is placed.
Excellent. Thank you. So I have a question that I think is for Kelsey based off of the question. It's from Xavier Nindum. Is there any motivation for the names like Comet or Planet or etc.? But I guess it could apply to any of your experiments.
There is a naming convention. So Comet is one of the oldest assemblies that we still have. And the person who designed the experiments, last name was Haley. So it became titled Haley's Comet because of the engineer who helped design it. And therefore, all vertical lift assemblies after that were named after celestial bodies. And there is a naming scheme. So a lot of times it does depend on the person designing the experiment, how they want to name them. They have a preference for, mythology or data scientists. They have to name things that way.
I forgot that Kelsey warned me that that is a can of worms, that question, but I thought that was a very concise and to the point answer. So I have a question from Kent Tart, and it says, how do you prevent radioactive exposure during these hands-on activities? I think it came during Jesse's presentation, but I guess it could apply to anyone. Gonna try, Jesse?
Yeah, sure. I'll take a stab at that. When it comes to ultimately, really, it comes down to which experiment it is, and you can take many different precautions, whether it be PPE. What we really focus on with ISA is that the fuel itself, the actual uranium, is dispersed within the fuel element. It's not leaking out. So that's how we get away with it there. When you talk about maybe the bare metals that you might see on something like tax, that's definitely PPE, or just having a fissile material handler handle it up until the point where, a student might manipulate something else on it. But planning, I guess, is the main way to do so.
So when Jesse says PPE, he means personal protective equipment. So, and he is correct that it varies heavily on the experiment. So at NSERC, we have stuff where we range where we just need to wear a lab coat and gloves just to make sure that you're not, touching something and then accidentally touching your face, or protecting your hands from stuff like that. And a lot of times it is to protect the material in those circumstances. But we also have experiments where we are working with bare uranium metal that oxidizes in open air environments. So we might be having to wear full respirators and bunny suits, coveralls. So where the person operating and handling the material is completely covered, that there's no skin exposure. We also have dosimetry monitoring in all those circumstances to make sure that we are not exceeding any limits that are allowed by the Department of Energy from safety regulations. We also do have other engineering controls. So the pressure of the room changes so that anything that could possibly be airborne stays into the room that you're operating within and doesn't move because of the airflow, because it's keeping it in that room that you might consider contaminated.
Just so you know, Kelsey, towards the end of you talking, I was getting lots of crackling, but I was still able to make out what you were saying. Okay, so I had a question that, here we are. This one's for David, I believe. It's from Robert Florian. It says, is the Sandia critical assembly under or over moderated?
Great question. So we've looked at a number of conditions, but the original grid plates, we have 4 different sets that we've used. Those have all been under moderated, but we've looked at increasing that pitch. And so we did that by using the same grid plates, but just removing every other row and column of fuel and effectively increasing that pitch. So we have looked at slightly over moderated, then identifying where that optimal moderation point is at. So typically they're under moderated.
Excellent. So I have two questions that come from Jeffrey Mann. I think they're both directed towards Kelsey. The first one says, what neutron sources are used in the subcritical assemblies? And the second question says, are the SPR3 plates used in any of the Nevada experiments?
So most of the neutron sources we use are Californium-252, which is releases a similar fission distribution, or neutrons of fission energies, similar to what we would see in uranium and plutonium. So that's why we use that source primarily for our assemblies. Then the SPR3 plates do exist within the NSERC inventory. These were the fuel plates that David mentioned that used to be at Sandia. However, they have not been used recently in any experiment.
Okay, great, thank you. So here's a general question. It says, what type of detectors are used for these subcritical experiments? And does anybody want to go first?
Sure, I can jump in. So at Livermore, we use helium-3 tubes. We have a couple different kinds, ranging from large, 3 foot long, maybe 1.5 inch diameter tubes, down to very small ones that are maybe 4 or 5 inches by 1/2 inch in diameter, but it tends to be helium-3. There's not any reason it can't be other detectors. That's just where our experience is.
And to add to that, at Sandia, we've primarily relied on fission chambers, and they work really well for our purposes. We have a number of them that we use. A few of them are hooked up to the plant protection system, but we have talked about bringing in some helium-3 tubes or different types of detectors, but up till now, we've primarily relied on fission chambers.
Here's a cool question, which I think is geared towards Jesse, but maybe not. You can correct me if that's wrong. It says, it's from Julie Esold. It says, how can the -70C experiment be bound for lunar applications?
That is a good question. So we're actually only looking down to -40C. The reason for that being transportation regulations, both in America and in Europe, state that, when you certify that fissile material is going to remain subcritical under all normal and upset conditions, the temperature they go down to is that -40. In terms of what we're looking to do with that experiment, though, is step it down. So start at room temperature, about 20 degrees C, and then take it at 0, and then -20, and then -40. So what we will be able to do is get a trend, and that's something that we could use to project out to -40. And also the capability itself isn't stopped at -40, just what we're looking at right now. The focus is down to that -40. So what I'd say is we might be able to predict down to it with the approach we're taking.
Thank you, Jesse. I have a question here. I think could be general. It's from Ronald Darrell Gachlian. It says, in systems where shape is very important, like a sphere, how do you integrate the detectors?
So a lot of times, if you know ahead of time that your experiment's going to be a sphere, you can integrate detectors by placing them centrally in the sphere and designing systems that allow for that to happen. So it can be a lot of engineering design. So our team here, while we design a lot of experiments from the nuclear side, we have a whole separate team of mechanical engineers who design all the structural components that go into these assemblies. So, and a lot of times we can also assume that the neutron leakage, so the neutrons that are coming out of our assembly, are proportional to the neutrons that are within the assembly. So a lot of times we will place detectors outside of the assembly and use that for our measurement systems.
Great, thank you, Kelsey. And so I have a question here specifically for David from Syed Kamal. And it says, Dear David, I'm going to paraphrase this as best I can, but it says that you mentioned the subcritical assemblies have low burnup. Is this different from subcritical reactors such as ADS or systems that are supposed to be used in some fission fusion hybrid reactors?
Yes, those are different. So the ADS, so that's an accelerator driven system. So that, again, that the power levels on those type of reactors much different than when these critical or subcritical assemblies.
Thank you. And also from Syed, it says, in which stage is the kilopower reactor? Is that for Kelsey?
So at this point, we at NSERC were involved with one of their initial test bed. At this point, we are no longer involved with the project. So I can't comment on the stage that that reactor system is in.
Got it. Thank you. From John Conant, we have, do any of your experiments do conformation measurements on delayed neutrons for various fuels? This one could be for anyone.
None of the experiments, at least that I spoke about, were for delayed neutrons.
This is a capability that, looking at some of these neutron physics measurements, is something we are working towards developing a larger capability for. We do frequently do these kinds of measurements on our critical assemblies. However, right now our inventory is set and it's mostly uranium and plutonium systems because that's the material we have available.
Evan, I think we have time for one more question. We're at 5:58 right now.
Okay, great. So I'm gonna choose an easy one then. So from Alejandro Restrepo, at what temperature do these experiments run? I know Jesse answered one about 40 degrees C, but does anybody else have any other temperatures they'd like to throw out there before we end?
At Sandia, we target 25 degrees C, so at room temperature, but we do have plans to look at temperature effects in the future.
And at NSERC, most of our experiments are done at room temperature. The facility is, well, room temperature and the facility is a little colder, so that's closer to 15 or 20 degrees C. But we have done experiments at high temperature, so, you know, in the 300 degrees C range.
Yeah, and to add one more comment for those TEX experiments that I mentioned with the uranium and plutonium. The uranium is just room temperature. There's no heat is being generated by fission. Again, it's just so low power. And for the plutonium ones, they actually do heat up. But again, that's not because of fission. That's because of the decay of the impurities within the plutonium that's actually heating it up. And they can get up to, Kelsey, maybe like 30, 40 C. Does that sound right?
Yes, at max 50.
All right, great. Thank you again to all of our panelists, David, Kelsey, and Jesse, and thank you to ANS, Janice, and Uchenna for putting this together. I'm going to hand it off to Janice in case she wants to make any announcements for ANS.
Great, thank you so much. This was really valuable, and I learned so much about, you know, your assemblies. I would like to invite everyone to register for our next YMG sponsored webinar on careers. This one is highlights women in trade and craft careers, and I dropped the registration link into the chat. And otherwise, that's it. Thank you, everyone.
Bye.